1 or 2 more minutes.
Okay.
If people are still joining.
Yes. Okay, so I welcome all of you for this last this series, week 3. I hand over now session to Dr.
Thank you, Dilpreet. Yeah, so this is the last lecture in this series. As you see, that there is a lot of there have been a lot of things to cover, and some of the things we have done very quickly, and of course, a lot is left. But I hope this enthuses you to read along these lines. So I am going to begin with presenting you some of the references which you might find useful if you're interested in studying this material and more around this. So of course there is this standard textbook Hoffman and Kunj which has all this kind of material, but not done in as great generality as I have been talking about, like working for arbitrary field. Usually it works to have a real or complex after a while. Um a good textbook to learn this kind of material and much more is this book by Roman, Advanced Linear Algebra. Uh, it's it could be a little boring to read this book because it is purely written algebraically. But if somebody is interested in knowing advanced linear algebra and all this kind of stuff, what we are doing and much more, we should certainly look at this book. And you can also look at somewhat easier book than Roman's book. This is Further Linear Algebra by Blyth and Robertson. It exactly covers the kind of material we have done in this last 3-4 days, um, and it's quite nicely and well written, and quite accessible even to undergrad students. So I certainly recommend this book number 3. Uh, which is basically part 2 of the book Linear Algebra, and it's called Further Linear Algebra. And of course, if you are interested in learning more about quadratic form, which is symmetric bilinear form, uh, uh, as I said, that it starts the base field starts playing a role, and a lot of things depend on base field. And so, if you want to, this is a little advanced book. I mean, people who are interested in working in this area or something like that, they can look at this book, Quadratic Forms by Lamb. And if you are interested in group theoretic side of the groups I define, uh, you can look at this book by Groove, which is Classical Groups and Geometric Algebra. This is quite nice, very accessible, and accessible to people who just know basic linear algebra. But it talks about this kind of groups and tries to prove that how you get simple groups, in fact. And it's very interesting book and accessible to even undergrad students. But yeah, it takes some effort to read this. It takes some time. Uh, if you are more interested in matrix group, going in the direction of Lie group or something like that, you can look at these 2 books, which are quite interesting. It has similar kind of title, what is called matrix group. by Baker and another book by Tapp. So yeah, you can look at some of these books. Okay, so let's begin with today's lecture. So what we have done so far, we defined what we mean by inner product space. Inner product space. And we said that we will be looking at two different inner product spaces. One were real and one were complex. So real and another were complex. And together we are calling them inner product space until unless I need to prove some theorem where I specifically need the property of the field real or complex, we'll simply call them inner product space. And we saw that there are some common properties. You always have orthogonal bases. So now onwards, I will assume, I will call, when I say a field F, I will mean F is either R or C. And whenever I say V vector space, then I always mean this is an inner product space. So inner product space. And it always comes with a form, which is inner product. Over real, we have non-degenerate symmetric bilinear form. Over complex, we have non-degenerate Hermitian form. And the particular one which are positive definite. So not anything gives inner product, but the one which are positive definite. So I'm going to assume that now onwards I have this setup. Okay, and we saw that there always exist orthonormal basis for such situation. There exist. This is quite important. There exist orthonormal basis. So let's move towards our topic. We are interested in understanding certain kind of operators. So if I look at set of all linear maps. Okay, so now I have started calling operator. Operator are same as linear transformation, linear map. Here we call, I'm going to call operator. The word operator is more used, of course, in something like function analysis and other things. So it's the same thing, linear transformation or linear operator or simply operator. So we are interested in understanding certain kind of maps in NV. Okay, not possibly all maps, but certain kind of operators which are in end V, and namely this will be called normal operators. So to define even normal operator, I need to first define what is called adjoint. So what I'm going to do, that given any t in end V, I will associate to it another operator which will be called adjoint. And using the definition of adjoint, I will define normal operator. Okay, so this is what I'm going to do right now. So to define adjoint, let's begin with, so this is what we need to define. We need to define this. Okay, so let's begin with what is called, this is a lemma, but this is quite important thing, and it's called a Reisz representation theorem. So the thing is that many of the things what we are trying to prove in this section or study in this section, in functional analysis, you will see that many of these things can be done for infinite dimensional situations, Hilbert spaces and so on. But here we are working with finite dimensional vector spaces. So most of the proof become much easier, much simpler than what you would see in Hilbert space setting in, let's say, functional analysis or something like that. Okay, so this theorem here is, for example, very simple as opposed to if you see this in functional analysis. But it is the same theorem. So that's why I'm writing it as a Reisz representation theorem instead of just saying it's a lemma. So what does this say? So let's begin some linear functional. Suppose I have linear functional in V. So the space of duals I write as V star. Then there exists unique vector V naught in V such that this f at any vector v can be obtained simply by computing inner product at that vector v naught. This will happen for all v in v. Okay, it's quite easy to see that if I fix a vector v naught and vary v, this is a linear map, right? And the thing is that all linear maps are like this. This is kind of very easy in some sense if you want to think about it, it's very easy thing uh, in the finite dimensional case, because what all I mean, okay, I can give you intuitive way of thinking about this. So given a linear product, if I fix first of the one of the variable, I can define a map from v to v star, right? So any in fact non-degenerate bilinear form, I think we described this earlier the day before yesterday, that this is equivalent to saying that this map is an isomorphism, right? So if I'm given f in v star and this is an isomorphism, then obviously it comes from some vector, right? It's as simple as that for finite dimensional situation. Okay, but in infinite dimension, this is not as. But let's do the proof by computation. I mean, this actually is a proof what I just said. But in any way, usually the linear algebra books would give you computational proof. So let's do that. So what I do is that I have to tell you exactly what we know, right? So my claim is that, so let's take v naught to be simply. So I know the value of f. Okay, so the proof will rely on fixing a basis. So let's fix an orthonormal basis. Fix an orthonormal basis of v, and let's say it is v1, v2, vn. This is an orthonormal basis. Then what I do is that I evaluate f at these vi's, and let's say I take its bar and vi. So the coordinates are going to be f of vi bar. Okay, so that is the vector v naught I take. And my claim is that this vector will satisfy the property. Okay, so to check that, we compute v comma v naught, and we'll verify that it's actually going to be f of v. So since I'm using coordinate, I will write v also in this coordinate. So let's say v is summation over xi vi. Then this will become summation xi vi here, and v naught is summation over f. Okay, just for changing the different variables, I'll say this one is vj, and then this will become now we have chosen orthonormal basis, right? So then you will see that all the cross terms will become 0. So the only thing will survive when I equal to j. Okay, so this will become only summation over xi f of vj bar. Sorry, I equal to j. So I cannot say uh, j. I should say same I. So let's correct this. So this is same I and vi. In fact, no vi is just a scalar. So why I'm writing vi? Yeah. So this is what it will come out to be: xi f of vi bar, and I equal to 1 to n. Now, if you compute f of v, you'll see simply from here summation over xi f of vi. Actually, so I have, if I am assuming this is a complex, then the bar should not be there. So that's why I'm not getting the correct answer. So this bar is actually not there because it's in the second coordinate, right? So when this comes out, there will be another bar and the bar will get cancelled. So that's what happens. So then I get these two things are equal. And that proves this lemma or this theorem, I want to say. Okay, so once I have this, now I'm ready to define adjoint map. So this is the theorem. So of course, as you realize in the theorem that I already assumed that V is an inner product space. So V is already an inner product space. And suppose I am given a linear transformation and V. My claim is that then there exists another linear transformation S, let's say in end V, satisfying the following equation, that if I compute T of V comma W, then this is equal to v comma s of w for all v comma w in v. Okay, this is very familiar equation if you know already what adjoint means. So what happens that I'm looking at the inner product, usual inner product. The first variable I change with some linear operator. Then that effect can be achieved by changing in the second variable, but some other linear operator possibly. And that linear operator will be called adjoint of the first operator. Okay. Let's prove that such a thing exists. In fact, this operator which exists will be also unique. And this will be the one which we will call T star. But I will define what there is the meaning of T star after we have proved this theorem. So let's prove this. So proof will use the Reisz representation theorem which we proved just now. So let's take any W. Okay, take any W in V. Now what I do is that I can define a map from V to F because I'm given T already. So I'll define this map to be take any vector, evaluate it at TV, and then apply W. Take the inner product with W. You see, W is fixed here, and V is varying, but T is linear. So this is linear in this coordinate. So clearly, this is a linear map. In fact, this is a linear map for any W, right? Is that clear? That this is a linear map for any W, and let's denote it for the sake of notation from to match with the previous theorem, Reisz representation theorem. That this is FW. Now I apply Reisz representation theorem. This will imply that there exists some vector W naught such that Fw of any vector V is given by the inner product V comma W naught. Right? This is what the Reisz representation theorem says. But Fwv, by definition, it is supposed to be just T of V comma W. All right. So you see from Reisz representation theorem, I can get W naught for any W. So if I fix one W, I get W naught. If I take another W, I get another W naught, right? So it's varying with the W. So since this W naught is varying with W, I will define, instead of calling it W naught, I can call W naught to be some S of W. So we define a function. We define a function S from the vector space V to V, where we take a W and apply the above process to get W naught. Right? So this W naught will be defined to be S of W. Now, my claim is this, that this map S, what I just defined, is actually a linear map. S is a linear transformation. It's a well-defined map, it's a linear transformation. I will leave this as an exercise to check. Once you check this, we exactly see that I have found S satisfying the property, what I wanted here. Okay, so this proves this theorem that I can find such an S. Okay, so now I'm ready to define what I call adjoint of a linear transformation. So this is definition. Definition is a definition of adjoint of a linear operator. Okay, so let's take a linear operator T in end V. If there exists unique linear transformation T star in end V satisfying the equation that T of V comma W is V comma T star W for all V comma W in V, then we say T star is, then we say T star is adjoint of linear transformation T. Okay, this is definition of adjoint. Adjoint is a linear operator which satisfies this equation, the equation which I have said here, this equation here. Okay, and what we just proved, the theorem which we proved just now, the theorem implies that for every T adjoint exists. Such thing may not be true if you are in infinite dimension situation until unless you are some nice situation. But here we are working with finite dimension, and we just proved that for every T there is an adjoint. Yeah. So as I said that, I mean, some if you have seen functional analysis, you might wonder that you require a lot of effort there to prove such statement, and here it comes out to be so easily. This is because we are in finite dimension situations where things become easier to prove sometimes. All right, so this is what I define adjoint. Now we are ready to define what is called a normal operator. So let's define uh, definition of normal operator. So the definition of normal operator looks a bit strange in at first sight. An operator T in and V is said to be normal if it commutes with its adjoint. T star is T star T. Okay. So it looks like, okay, we can't say much about such kind of operators because the equation looks very strange. Thing is that this kind of operators include many well-known examples. So let's write down examples of normal operators. That is where usually the normal operators are applied in some sense. So the first example is what we call self-adjoint operator. Self-adjoint operator. Self-adjoint operator is the one for which T is equal to T star. So you can easily check that if T is equal to T star, it will satisfy T star, T is T star, right? Uh, if you recall, uh, in yesterday's lecture, I defined what is called Hilbert operator, right? So this operator, uh, in the case of real, this is nothing but what I called symmetric, right? And in the case of complex, this is what I call Hermitian. So if we understand normal operator, we can also say something about symmetric matrices or Hermitian matrices or Hermitian operators, right? That is the first example. In fact, second example, let's say, so example number 2, what is called skew self-adjoint. These are those operators for which T is minus T star. Okay, and this includes the example of skew symmetric when we are working over R. This is nothing but the skew symmetric, and over complex, what you might call skew Hermitian. Okay. And the third, quite important example which it includes is what is called unitary operator. So when it is real, wait a minute, right. So the more generally, this is called unitary, and the unitary operator is the one for which T into T star is identity. and which is equal to T star into T. All right. But if you follow the notation what I defined yesterday, in the real case, this is what you call orthogonal matrices or orthogonal transformations. In complex case, I called it unitary. However, here you can together call them unitary if you're just working with inner product space. Okay. So if you understand, so what we are going to do is that we want structure of a normal operator. Right? If you understand the structure of a normal operator, in fact, we can conclude things about also these three kind of transformations, right? These three kind of operators. So let's aim to understand normal operator. It turns out that normal operators, actually, they look quite strange to define with, but they are not actually very, very strange. What do I do? Let me give an example. Let me give you an intuitive reason why they're not as strange as they look like. Okay. So here is some intuition for understanding only. So what do I do is that suppose I have in a product space V, we have orthonormal basis, right? Orthonormal basis. So I can assume that matrix of, so I'm going to think in terms of matrices. That is where my intuition is going to come. So matrix of inner product, I can think of is identity. Because I fix orthonormal basis, then the matrix will be identity matrix, right? And now the question is that in this, in the matrix version, what a normal operator is, right? So what can we say about matrix version of a normal operator, right? So what can we say about a matrix version of a normal operator? Uh, so So what is the equation of normal operator? Equation of normal operator is something like TV comma W is V comma T star W for all V comma W in V. So let's say let matrix of T is A and matrix of T star is suppose A star, and I want to find the relation between A and A star, right? This is what I want to do. So I have fixed a basis, an orthonormal basis, and we'll write V in orthonormal basis as XI VI, basically column vector X, and W to be YI VI, column vector Y. So then you will see that, I mean, now we are used to doing this kind of calculation, which I have done already in last 2-3 lectures. So I will just quickly write it down. So this will become basically AX transpose, then the matrix of the form, which is supposed to be this identity matrix, and then W, the column vector is Y. Okay, and now the right hand side is actually I should put here bar. So because I'm also including complex case, so this is Y bar. And the right hand side is going to be X transpose and the matrix of the form, which is identity, and I have to get the matrix of T star W. So T star is the matrix of that I am calling it A star, and W will correspond to the vector Y, and then bar here, right? And this happening for all X and Y, all column vector X, Y. And now again, I had given an exercise. So okay, let's just this rewrite. So this is X transpose, A transpose, Y bar. This is simply X transpose, A star bar, Y bar. Okay, and then I had given this exercise that something happening for all xy, then the matrix between them are same. So this will tell me that A transpose is A star bar, which means that actually the matrix A star can be obtained from A by simply taking bar transpose. Okay. So often in basic textbook, they tell you that the matrix of normal form is always, the matrix of adjoint A star is always A bar transpose. This may not be quite correct actually. They always confuse that we have fixed an orthonormal basis. Sometimes they don't say that explicitly. So if you don't fix an orthonormal basis, there will be matrix of the inner product also going around here. So this will be conjugated by the matrix of that inner product. So this is one of the confusing points. So this you can do only when you already chosen an orthonormal basis, which may not be true if you're not working with inner product positively definite. If you're working with more general form, then that may not be true, for example. So okay, now I have found a matrix of adjoint. So the matrix of adjoint is going to be A bar transpose. And if I wanted to say something is normal, so normal would mean that uh, that I have A star is A star A. That is A bar transpose is A bar transpose A. Very good. Okay, now suppose, the intuitive reason what I wanted to understand that what normal matrices could look like. Suppose I'm working with complex for a moment. Let's assume that I am working for complex case, right? Then I can conjugate A to always an upper triangular matrix. So let's take very simple example of 2 by 2. Let's say I have ABC. This is the matrix A. Then matrix A bar transpose would be simply A bar, B bar, C bar. So the thing is that this equation here, the equation of normal, says that certain upper triangular matrix commuting with certain lower triangular matrix. What are the odds of happening that? Okay, so I'm just doing the 2 by 2 calculation to show you that it's very rare. So let's do this. A, B, C, and I multiply with A bar, B bar, C bar. So this I'm computing A star. This is going to be A bar. So you have to quickly compute this B, C bar, C, B bar, C, C bar. And this is supposed to be, this matrix is supposed to be equal to A star A. So this is supposed to be equal to A star A. And A star A would be A bar, B bar, C bar here, and A, B, C here, which will give me, this is A bar B, B bar A, B bar B plus C bar C. Okay. Now look at this entry here. This will imply that B bar B is 0, which means B is 0, right? That exactly means the matrix is diagonal. So this implies A must be diagonal. And this is no surprise. This is what the structure theorem is. In fact, it will turn out that normal operators are close to being diagonal. In fact, over complex, it is diagonal. Over real, it is almost diagonal. Okay, so this is what the structure theorem would be, in fact. Okay, so let's actually prove this. It requires a little bit of like preparing background to prove this result, which I'm trying to tell you, which is the structure theorem of normal operators, which is also called spectral theorem. Okay. So let's prove this. And to prove this, I need to prove several results about normal operators, which are generally very easy to prove, but one has to go step by step. There are several ways of proving this, in fact. So I'm going to follow the proof, which involves, something to do with polynomials, the kind of proof I gave for Jordan canonical form or something like that. So I like that kind of proof. So I'll give you a proof which involves that kind of idea. Okay. So I'm going to prove several properties of normal operator, which will lead to the structure theorem. In fact, once we prove this property, structure theorem will be just corollary of that. So property number one, some easy property. Property number one is, so what I am assuming, so I am given, so let's write in one go, given T is a normal operator. Okay, so in all these properties, I'm assuming T is a normal operator, and then I'm going to write the property further. The first property is that if T is normal, T star is also a normal operator. So this is obvious because T into T star is T star into T, and the same equation gives you T star into T is T into T star. So this is an obvious property. Second property, uh, T inverse, if it exists, is also normal. You can check this. I'll leave this as an exercise for you to verify this. A similar kind of property. T inverse is also normal. Okay, now I come to a little more interesting properties. Third property is this, that suppose uh, fx is a polynomial in fx, then I can substitute t. So f of t is also an operator. Claim is that f of t is a normal operator. So if t is a normal operator, any polynomial in t is always normal. And proof is actually kind of very easy. To prove this, I have to prove that ft into ft star is ft star into ft, right? So what does this mean? This means if I expand this out, so suppose f of x was something like a0 plus a1x plus a2x square plus so on, a n x to the power n. What does this mean? So if I say ft into ft star, I have t square and t to the power n. Ft star would be t star square t star to the power n. Since t and t star commute, I can at each step write t star before t, and I will get exactly ft star into ft. So if you just write it down, you will get this answer. So for example, if I just wanted to do degree 1, uh, example, for degree 1, a0 plus a1t into a0 plus a1t star. So if you expand this out, you will see that uh, uh, the expansion will match with the expansion of using t star t is t, it will match with a0 plus a1t, right? So it's just simply writing down in longhand. Okay, so let's get to the property number 4. So this is property 4. So the property 4 is this, that so I'm always assuming t is normal. So t of v comma t of v, if I calculate their inner product, it is equal to t star v t star v. Okay, and this will also give automatically that norm of t of v is always equal to norm of t star v, right? So proof, this is quite easy to prove. So let's prove this. So what is t of, let's take the left hand side, t of v. This is going to be, I can take this t on this side as star, so I get this t star t v. But I know that t is normal, so now I can commute this t and t star here. I can write this as a v comma t into t star v. Now I can take this t on the left hand side, so I get t star v comma t star v. So this proves the this fact. Okay, so let's prove property 5, and this is quite interesting property and important property. This is the only one which will require a little bit of effort in proving this property. So the property is as follows. There are two parts. Number A, kernel of T and kernel of T star are same. Okay. Not just that, property B is that kernel of, if I look at t square, it is going to be same as kernel of t. In fact, it is same as kernel of any t to power k for k greater than equal to 2. Okay. In fact, 1. I mean, all kernels match. So this is very useful property, and this is what is going to help us achieve the structure theorem. So let's prove this. This requires a little bit of effort. So we'll prove this. The proof of the first part A is easy to prove from the previous one. So suppose I have a vector v which is in kernel of t. Okay, that means t of v is 0. But if t of v is 0, norm of t of v is 0. But from what I proved in part 4, this will also imply norm of t star of v is 0. Because norm of t v and t star v is same, which will imply that t star of v is 0 in fact, because I have inner product, right? And everything can be reversed here, so I get if and only. So that proves part A. The part B requires a little bit of proof, and let's do that. So proof of part B, we'll do in 2 steps. So step 1, let's do step 1. So step 1 says that this is also a property of normal operator. So since T is normal, I can get decomposition of my vector space V as kernel of T direct sum. In fact, it is perpendicular to image of T. Okay, so T almost behaves like a projection operator. That's what it means, but we'll not go in that direction. I just want to prove this decomposition. So to prove this, I'll claim this. So claim. So I'll prove in 2 steps. So claim. First, of course, kernel of T intersection image of T is 0. And I also prove that image of T perpendicular is actually equal to kernel of T, right? So then you see that it's a direct sum and they're orthogonal to each other. The second part will imply that also. Okay, so to prove this, it's quite easy. Suppose I have vector v which is in kernel of T intersection image of T. That means T of v is 0 on one hand, and v is an image of T, so v is also T of some other vector, let's say w, right? But this together will imply that norm of T of v is 0, because T of v is 0. Wait a second, what I'm saying. Yeah, okay. So since norm of T of v is 0, this will also mean norm of T of, it's also in, v is also an image of T, so v is T of w. Okay, so I will write it here. I actually wanted to get okay, I will not. Okay, I'll come back to this later. Let's move to this next step, and then I'll come back to prove this later. So this part is still to be proved. Let's first prove the second part. Maybe that will help me to prove the first part. So what is the second part? I have to prove that image of T perpendicular is kernel of T. So I'll prove both way that this is contained in this and this is contained in this. So suppose I have a vector v which is in kernel of T, and I'll prove that this implies v is in image of T perpendicular. How do I do that? So V is in kernel of T. So obviously I have T of V is 0. To prove it is perpendicular to everything in image, I will take V, I have to compute V comma something in the image. So let's say something in the image is of the form T of W. But when I write this, I get also T star of V W. But if T of V is 0 from the previous step, you also see that this will give me T star of V 0. Because the kernel of T and kernel of T star are same, right? So then I get here 0 comma W, but then 0 comma W is 0. So this proves this. Similarly, I can prove the other ground. Maybe I'll leave it as an exercise. So exercise. Okay. So this proves basically, okay, this was step 1. I have to still prove the step 2. So step 2 is the final proof. So let's say that I want to prove that kernel of T square is kernel of T. All right. That means I want to prove that if I have vector V in V such that uh, T square of V is 0, this would be if and only if T of V is 0. Of course, if T of V is 0, then T square of V is 0. So I need to prove in this direction. This is the question mark. Okay. So, okay. So let's write W equal to T of V. If I write W equal to T of V, I see that T of W is 0. So this means W is in kernel of T. And of course, W is T of V. So this implies that W is also in the image of V, image of T. But then if something is in the image of T and kernel of T, we just prove that the intersection is 0. So that implies W is 0. Right? So so this proves that the kernel of T, T square, and all these are same. So, okay, now we come to the crucial step, which will tell me actually these operators are almost like a diagonal operator. So this is the property 6, and the property 6 says that the minimal polynomial mtx of a normal operator T is a product of distinct distinct uh, distinct monic irreducible polynomials. This means that if you factorize mtx, that is, if you factorize mtx as a product of irreducible polynomials, p1x, p2x, then there are no powers, prx. Then there is no power here. I mean, the power is always 1. And if you remember, when we say some operator is diagonalizability condition, uh, we proved that if I have, for example, I mean, let's say you are working for algebraically closed field. If I have an operator which has all eigenvalues appearing with multiplicity 1 in the minimal polynomial, that means minimal polynomial is product of linear factor, then that is certainly diagonalizable, right? So if I think of applying that theorem on after knowing this operator, I can say that these are diagonalizable. But that theorem will not immediately give me the structure theorem because I want to do little more than what that theorem will give. So we'll see what more I want here. But this almost says that the operator is diagonalizable. So let's do the proof. So the proof of this follows from what we did just now. So suppose minimal polynomial mtx has some polynomial appearing with degree more than 2. So the separate out that polynomial P and put other things together as QX. Okay, let's do this. By definition, we know that the minimal polynomial MTT will be P square T QT here, and this applied to every vector V is 0. This is the definition of minimal polynomial for all V in V, right? Because we said that when we substitute T in MTT, it's identically 0, meaning on every vector, it becomes 0. Okay, since T is normal, one of the property in very beginning we said that any polynomial in T is also normal. So if I look at MTT, this is also MTX is a polynomial, so I substitute T. This is also a normal operator, right? Similarly, if I apply so now actually I want to use this one here and apply the previous step. So we will take P of T. This is also a normal operator, and P square T of something is 0 if and only if, this is what we proved, the T square of something is 0, then if and only if T of V is 0. Kernel of P square T and kernel of PT is same. So this will mean that PT into Qt of V is 0. I'm applying the previous property which I proved just now, that the kernel of T square is same as kernel of T. So instead of T, I am taking PT as my normal operator. Then kernel of P square T is same as kernel of PT, right? But this will imply, this happens for all V. This implies that PT into Qt is minimal polynomial. Which is contradiction, because I assume that minimal polynomial is P squared T times Qt. So that means no higher power can appear in the minimal polynomial. This proves that fact. All right. So now let's prove a couple of more properties. The next property is, so this was number 7. It's going to be 7. The next property is that if I have a vector which is an eigenvalue of T, then the same vector remains eigenvector for T star with respect to lambda bar. This is important. The vector is same. So if I find one eigenvector for T, the same vector remains eigenvector for T star. So the eigenvectors are same for T and T star. Okay. The eigenvalue changes by lambda and lambda bar. So the proof of this is quite easy. I can look at, I wanted to know what is the kernel of T minus lambda, right? Kernel of T minus lambda. V belongs to this, right? And then this side, it is kernel of T star minus lambda bar. And I want to say that V belongs to this. So somehow we want to say that kernel of T minus lambda and T star minus lambda bar is same. And this follows quite easily because we said that kernel of T and kernel of T star are same. So instead of T, I will take T minus lambda. So from that statement, I get kernel of T minus lambda is kernel of T minus lambda whole star. But if I apply star on the sum, it becomes the star of the first and second. So this is kernel of T star minus lambda star. Lambda is a scalar matrix. It is star is just lambda bar. And this gives me this property 7. Okay, so let's prove the property 8. Property 8 is also interesting. This is where I was saying that I will use some property of polynomials. So suppose I have two polynomials, fx and gx in fx, and I assume that f and g are coprime. F and g are coprime, and I find a vector v and w in V, which is killed by f and g respectively. What does that mean? That means if I apply f of t on v, I get 0. And if I apply g of t on w is 0. So suppose I ft, remember this is what I was defining the other day, cyclic vector. When I was trying to define cyclic vector, then I had defined what is called annihilator of a vector. So this is like, suppose I find a polynomial which annihilates v, and I find another polynomial which annihilates w, but these two polynomials turn out to be co-prime, then the vector v and w are perpendicular. This is kind of a very interesting consequence of that. We use this kind of thing when we're trying to prove not cyclic decomposition, primary decomposition. So it's analog of that here in general setting. So let's prove this. The proof of this. So since f and g are co-prime, using some ring theory result, it will say that there exists some a, there exists a and b in fx, such that ax fx plus bx gx equal to 1. Now I will apply use the operator t in this equation. So I get this equal to identity operator. Now I evaluate it on the vector v. If I evaluate this on the vector v, then I'll see that the first component, this is identity of v equal to v. This first component, this becomes 0 because this is what I am given. Okay. Now let's compute inner product of v into w. What I do is that I substitute this value of v from this equation what I have got. So this is bt gt of v comma w. But now what I can do is that I can take gt on the other side, because of course gt is also an operator. So there is a star of that, right? So bt of v and gt star w. But we know that since t is normal, t star is normal, so gt star is also normal. This is also normal. And for normal operator, kernel of gt and g star t is same. So w is being killed by gt, so it's also killed by gt star. So this part is 0. This becomes 0. So this is bt of v comma 0, and hence I get 0. So this is why v and w are perpendicular. And finally, simple fact I want to write here, which follows from this is, let's write this also as this is problem number 9. So suppose I have lambda and mu distinct eigenvalues of t, then the eigenspaces e lambda is perpendicular to e mu. And this follows simply from the previous one, because to get the eigen space E lambda, we compute kernel of T minus lambda, and to get E mu, we compute kernel of T minus mu. But we can apply the previous step for the polynomial fx to be just x minus lambda, and the polynomial gx to be x minus mu. Since lambda is not equal to mu, these two polynomials are co-prime, and hence whatever vectors that is killed by t minus lambda and the vector killed by t minus mu, they are going to be perpendicular. So this proves quite. So I'll just take another 5 minutes to write down now the final statement, because it just follows from now all the things what I have proved here. So this is what is called structure theory or spectral theorem. So spectral theorem. Or simply this is called a structure theorem of normal operators. So I'll write the two cases separately rather than mixing up together, and otherwise they look very complicated. So in the complex case, suppose I have V is inner product space over C, and suppose I have T normal operator, then then uh, then V can be written as direct sum of its eigenspaces E lambda R, and T is simply identity, so lambda 1 times identity plus lambda R times identity. That means if you choose these eigenvectors as a basis, then the matrix of T will look like simply lambda 1, lambda 1, lambda 1, and so on, then lambda R, lambda R, lambda R. Means it actually looks like a diagonal. Okay. In real case, in real case, it's little more than that. In real case, so I have V inner product space over R, and again T is normal, and then V can be written as orthogonal direct sum of if there are eigenspaces, then orthogonal direct sum of eigenspaces E lambda R, and there could be some more subspaces, but each of these other subspaces are going to be only dimension 2. So these are eigenspaces, and these ones are going to be uh, dimension 2 cyclic uh, spaces corresponding to quadratic polynomials, degree 2 polynomials. Okay, and moreover, so the question is that how does T look like? So in fact, let me write T in the matrix form. If we choose appropriate basis, meaning basis with respect to that decomposition what I just wrote, matrix of T will be something like this. So there'll be first of all some eigenspaces lambda 1, etc., and then lambda r. Then there will be 2 by 2 blocks. So there will be 2 by 2 blocks. Okay, so this is how the matrix of T will look like, and the proof of this follows from what we did just now. Because suppose we are taking the complex case situation. So in the case of case 1, in the complex situation, let's look at the minimal polynomial of the normal operator. Minimal polynomial of normal operator. They were complex, so there are eigenvalues, right? But we proved that for normal operator, no irreducible factor appears with degree more than 1. So each one of them are just going to be x minus lambda 1, x minus lambda 2, and so on, x minus lambda k. And the last step, what I said, that eigenspaces are going to be perpendicular, we'll just simply give this proof. Okay. What happens in the real case, the case 2? In this case, I take the minimal polynomial. So this minimal polynomial will be polynomial over R. Now it can have degree 1 factor, and it can also have degree 2 factor, right? So it can have also some other P1x up to Pmx. These one will be degree 2. These one are going to be degree 2 irreducible polynomial. And these are the ones which give you that 2 by 2 block. Now you have to just simply write the spaces corresponding to each one of these are also going to be orthogonal by the last property, and this will give the proof of that. And now you can apply this to get structure. Now we can simply apply this theorem like this to get uh, orthogonal matrices and unitary matrices up to conjugacy. And they will look like exactly what is written here in the theorem, because we just saw that orthogonal operator or unitary operator, they are normal operator, and this statement here will say that any unitary operator is going to look like a diagonal. In fact, its diagonal entries will turn out to be certain complex numbers of norm 1. That is simple checking, you can do that. And any orthogonal matrix is conjugate to a matrix of this form here, which has some diagonal entries and then some 2 by 2 blocks on the diagonal. In fact, these 2 by 2 blocks will turn out to be the matrices, what is called rotation matrices: cos theta minus sin theta, sin theta, cos theta. But okay, I can explain maybe a little more, but anyway, there is no time. I hope you get my point here. Okay, thank you. So if you have any question, you can ask me.
Any question, participants? Okay, so
Yeah.
lecture of Anupam sir. So I thank you very much for this wonderful series of lectures.
Thank
So
you.
from participants, anyone would like to give any feedback to sir?
Sir, thank you so much for these lectures. These things
Thank
are
you.
very important, and the approach that many things you at many places you use group theory concepts. So those things are very nice. Thank you for
Thank you.
the lectures, sir.
Thank you. And enjoy other lectures. And if you have any question or doubt, you can also write to me. You can find my email ID on my webpage or somewhere. And if you have any question or doubt, you can write to me later also. Thank you, everyone.
Sure, sir. Thank you so much.
So is there any other question for sir? So thank you very much. And
Yeah.
we will start
Thank you.
tutorial after 15 minutes.
Yeah, sure. Thank you.
Okay.
Ma'am, at 6:15 we will start, na?
Not 6:15. After 15 minutes. So we'll start
Okay,
at
okay.
5:25.
Okay, I heard after 5 minutes. Sorry, ma'am. Thank you.
Okay. So I'll continue tutorial from the same meeting.
Okay, thank you, Dilpreet.